Okay, this is where we stopped. Just kind of spontaneous versus not spontaneous. Just something happens on its own. Spontaneous doesn't happen on its own. Not spontaneous. Redrew the skull and crossbones because that was a pretty bad looking poison symbol. So there you go. All right. Now we're taking a look at kind of how you can predict this, and the way you predict it in a reaction, and you're going to have to do this, is that you're going to be predicting, okay, what is happening to S. So if the S is going towards disorder or more disorder, then that's positive, and if it's going away from disorder or becoming more ordered, then that's negative. So that's kind of how we're going to look at things. But the easy way to look at it is this: if you kind of have a, a scale from solid, liquid, and then gas, as you go towards the gas phase, the particles are spreading out. They are random. They get to kind of bounce around wherever they want. When you go towards the gas phase, you're going to go towards more disorder, more randomness. And so that's going to be a positive delta S, more random. As you go towards the solid, the particles clump together. They become they have less movement, and they are more ordered. So we have less disorder. So think of a positive delta S as more. That's what a plus is going to give you, more randomness or more disorder. So if you look over here at the chart, if you had a solid to a liquid, okay, the liquid is more, you're going this way. You went from solid to liquid, so you're going to go towards the plus sign. All right, and so that's where we get the positive delta S. And you can do it with any of the changes in states of matter, but this allows you to predict the sign, maybe not the number, but the sign of delta S without doing any kind of math or having any kind of numbers. So it says ice has less entropy than liquid water. So we're saying that ice would have a lower delta S and the liquid water would have a higher delta S. And then water vapor has more entropy, so it has the positive, more S, more randomness versus less randomness. So that's the way you want to think of it. So right here, super duper, it says super duper thing, liquids are more ordered and have a lower entropy than gases, which are less ordered and have a higher entropy. So it's all about that delta S sign. So, okay, entropy is a state function, so it's going to be dependent on states of matter. So it depends on the state of matter. So that's why we're looking at solids, liquids, and gases. And it also depends on amount. So once again, coefficients are going to be important, and per mole. So we're looking at things in terms of how much you have. So it says both delta H and delta S can help you determine if something is spontaneous or not. And so that's what we're going to be doing. So the change in entropy or delta S is positive. We're just kind of going over this again and again. If disorder increases, or negative if disorder decreases. And I think that this idea up here that I did up here, I think that does the best job of explaining that. Just the idea that we're going towards the gas phase, more randomness, more disorder. If we go towards liquid phase, we're going to go in the opposite direction. So I think that works out as best for students. Okay, here goes some examples. And so it says liquid to solid. Okay, makes sense. Liquid to solid, we're going towards solid, so we're getting the negative, less randomness, less disorder. So always think of it in terms of randomness. So if you think of it in terms of order, then it all gets messed up. Liquid to gas, okay, so liquid to gas, positive because we have more disorder, so more disorder, right? So like that's how I'm thinking about it, or randomness, particles bouncing around. Solid to liquid, liquids get the, once again, if you got the solid, liquid, gas, this is the positive delta S, this is the negative delta S. That's how I would think about it. And then this one here is interesting. Aqueous, you want to think of aqueous as a liquid. So we had a solid and a liquid go to a liquid and a liquid. So we have more particles on the right side that are disordered. So that's just kind of how that one works. And this one, we start to count moles. And so if you look here, they're all gases, right? So that's a gas, and that's a gas. But now we can count. So the left side, starting chemicals, we had 1, 2, and 1. So 3. So this side has 3 moles that are gas. And this side has 2 moles of gas. And so what happened is we lost a mole of gas. So if you think about it, we're actually going away from the gas state of matter because we have less of it. That's what's happening in this example. So we have a negative delta S because we lost a mole of gas. So you just compare moles on one side to moles on another if it's the same state of matter. So 1 mole of gas is lost. That's really pretty important because this does come up quite a bit. There we go. All right. So you can either just look at states of matter. If you go towards the gas phase or away from the gas phase, you can figure it out. I think using this concept, this chart right here, just what I'm doing there, I think that's really helpful. So that's kind of what we're doing. Okay, you guys are going to try this a little bit on your own. So here we go. Try these on your own. You've got example 15 here, and then you also have example 16. So try those, pause the video, and what I'm looking for is, so write down, is it a plus delta S or is it a minus delta S? Do I have more randomness or less randomness? All right, let's take a look. Here we go. So gas, gas, gas. Okay, so this side has 4 moles of gas. This side has 2 moles of gas. And you're like, well, how the heck does he tell how many? Just the numbers in front. That's a 1, that's a 3, that's a 2. So 4 on the left, 2 on the right. So if we write down our line, gas over here, solid over here, liquid in the middle. This is a plus delta S if we go that direction. This is a minus delta S if we go that direction. So we had 4 moles of gas, but now we only have 2. So if we think about it, in terms of our arrow, we're actually going this way. So we have less moles of gas. So the delta S here is less randomness. So that's going to be a negative delta S. Okay, so you can kind of see kind of my thought process there. All right, let's switch pen colors here for this one. Okay, so this is a solid, and this is aqueous is the same, remember, as a liquid, so it would be kind of like right there. So it went from solid to liquid, so that's going to be a positive delta S. And then this last one here, liquid to solid, so we're going this direction, liquid to solid, and so negative delta S. Okay. All right. Let's see how you did on 16. Same general idea. I mean, these aren't really, they don't really change much. You just look at states of matter. But there was one that was a little tricky here, so let's see how you did. Okie doke. We've got, change our pen color here, gas, gas, and it turns into a solid. So that's pretty easy. We are going from gas to solid. We're going this way, negative delta S. We're going away from the gas and we're going towards the solid, right? So like that concept right there. Okay. A solid turns into a solid and a gas. Okay. So you could look at this a couple of ways, but you have more moles of gas on one side than the other. So we're kind of shifting this way. We're going towards gas. So that's going to be up more randomness. So it's a positive delta S. And the last one, gas, 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 gas. We got to count moles. So we're going to have to count the moles. So let's go ahead and look on the left side. This is a 1. This is a 1. So there's 2 moles on the left of gas. And same thing there. So this one is a question mark. You know, you cannot determine this with inspection. You would need to look up actual numbers. Like you'd have to get out some a set of data, and if you had a set of data, you could look these up and figure out exactly what their numerical values are. But this one cannot be solved without more information. So we cannot solve this one here without more information. It's just can't do it with just looking at it. All right, so there you go. And what are we going to use this for? Well, the sign on this delta S is going to become extremely important when we start doing the math problems, because if you have the wrong sign, then of course answer gets a little in the incorrect side. So here we go. Guess what? We have another item that we can solve numerically, the S, but it solves the same way. Products minus reactants. So I'm going to end up stopping here, but just what's going to happen is we're going to do the same thing we've been doing, products minus reactants. We're just going to substitute in a new value, S, but see, it also has values we can look up on the charts in products minus reactants. Not a big deal. The one thing that's different is this is in joules, and that is going to be a bit of a